All right, welcome to Module 17B, more on linear regression. This is the last lecture of the course. And this is kind of a miscellaneous lecture. I'm going to talk to you about some caveats with using linear regression, how we go about checking the assumptions are met by our data set, some extensions to linear regression, and a really important phenomenon called regression to the mean. So these are all important points, but they're each one of them sort of too short to break out into its own video. So thought I would just combine them all here. So starting with the caveats or things you need to watch out for. Just a couple of these really quickly in case they didn't come through in the previous lecture. First of all, you need to pay attention when you see an analysis using linear regression and you see a confidence interval or you see a graph like either one of these two. You need to pay attention to what the confidence is about. Is it about the slope and the intercept, or is it a confidence statement about where the points fall out? Obviously, we observe the data points, so we have no uncertainty about those. But one of the nice things about regression is you can use it to predict values of the response variable for new values of the explanatory variable that you haven't observed. So over here on the left, we see confidence bands, which show the uncertainty related to our parameter, beta, for the slope of the line. So we're not exactly sure what beta is, and so there's some uncertainty there, and that gives us a range of possible lines that are plausible lines. And so this sort of hourglass shaped curve around the line that's dashed gives us a sense of that uncertainty of where the best guess for the slope might fall. But if we're interested in predicting a particular data point, like what's going to be the most probable value for the age in years based on the proportion block, I don't even know what this example is. It is from your text. I should have looked up the context here. Around here, that's the best guess. But based on the scatter in this plot, there's sort of a normal distribution around that point, and it's quite plausible. You know, there's at least a 95% chance, or we're 95% confident that a point, if we just selected one at that value, would fall in this range, but it's also possible to be out here as well. Since there's uncertainty about the slope, but there's also uncertainty about how much scatter there is around the line, we have generally much broader bands, confidence bands in this, much broader prediction intervals than we have confidence bands. So confidence bands is the statement about the slope. Prediction intervals are the intervals to visualize where you can be confident that a new data point would fall if you sampled it. And so there's more sources of error over here on the right, and so there's a wider prediction interval. Okay, so that's one thing to be aware of, that distinction. Another common problem with using regression is extrapolating beyond your data set. So this is an example also discussed in the book where they're looking at the length of the ear versus the age of someone from a population. And so ears, because they're all cartilage, they continue to grow throughout the life of individuals. So you can do a linear regression. That's not a bad fit for a straight line, really. But if you continue to use that regression on beyond the measurements in terms of the ages in the study, you get some really implausible values of large ears on newborns, or if you even think about it sort of in fetal ear length and stuff. Those are totally implausible values because in order to, at some point, this relationship is nonlinear. And so out here, we call that extrapolation. We're going an extra distance outside of our data points, whereas linear regression is really good in interpolation, giving us predictions between our data points that we've observed. So we can be pretty confident in the interpolated predictions. Obviously, we have uncertainty like this prediction interval here, but we really don't have any statistical analysis of what's going on outside that range. We don't know that the relationship continues to be linear. So sometimes you'll see people report extrapolations in scientific papers, but when they do, it's really important to be very explicit that like it's assuming that this linear relationship holds and things like that. So there's no data behind that per se. It's an assumption that the linear relationship that holds up here is going to continue to hold down here, and that can be a really questionable assumption in many cases. So that's something to be aware of. Just because you can make a prediction based on the line, once you're out of the bounds where the data fall, you really don't have a lot of confidence in those predictions, or you shouldn't have confidence in those predictions. All right, so how do we go about checking whether a data set fits the assumptions such that we can use linear regression and feel confident in its results. This is a slide I put in the previous lecture just to review the assumptions again. The assumptions are that for each value of x, there's a population of y values. The expected value is the line that we're going to infer with linear regression. It's got some intercept and some slope, intercept alpha, slope beta. And specifically, it's not just the expectation is around that line, but the assumption is that the y's are normally distributed around that line. So the slope, the line gives the expected value of the normal, and there's some scatter described by this standard deviation for the normal, which we don't know a priori, but we can learn something by looking at the scatter around the line. And then another assumption is that the distribution of y's around the prediction line, it's got the exact same spread for every value of x. So we don't have different sigmas for different x's. So the spread in y conditional on some value of x is just the spread in y. It's just that sigma parameter. So it's supposed to be the same sort of normal distribution over every part of the line. And then we assume that we're just drawing yi's randomly from the normal distribution. So we're just randomly sampling according to the x value we've chosen. So remember, there's no assumptions about x, so we don't really have much to check there. But we need to verify that these assumptions hold. And they're a little tricky to think about. In correlation, we assumed a bivariate normal, so you could look at the distribution of the y's and the distribution of the x's, and they should both look normal. But here, the y's should be normal, but they're not normal around one particular value. They're normal around a line, so if you look at them without paying attention to the line, they're not going to look normal, and that could still be okay. So here's the assumption sort of graphically. I sketched out something like this in the previous video, but this is from your text, does a much nicer job. For each x value you choose, there's some kind of prediction line, and really the assumption is that there's a normal distribution around that line. So it's possible you'll get values of y up here or down here. They should be, most of them should be pretty close to the line, but we don't know what the standard deviation of this normal is, but it should be the same normal up here as here, as here, as here. So there should only be one kind of spread across the line. That's an assumption in how the calculations are derived for linear regression. So here's the example that we looked at last time with the temperature versus latitude for a fish, looking at geographic distributions. And this was the regression line. This was our least squares regression line, or a linear regression line. We had a slope of 1.109. We had a y-intercept of 50.37. So those are our small number of data points and the best fit line there. I looked at, this is a slide also from the previous lecture. We looked at how to calculate the residual error, and we walked through all those procedures. Remember what the residuals were. We had the raw data and the means of those, but these y hats, those are the predicted values. So based on each x, there's a predicted y value. I'm going back a slide. So it's, if we plug in that x here, we get a prediction of where y would fall. So that's exactly what's on the line. So basically this is calculating the y hats are what is the value of the line at each of these points. So y hat for this one would be right on the line here, y hat for that one would be right on the line there, etc. So we just go through all those calculations, and those are all our predicted points. And the residuals, remember, were the difference between the actual y value and the prediction. So yi minus the predicted value. So these are the residuals, and these are the things that are supposed to be normally distributed regardless of what the value of x is. So one really useful way to detect whether your data set is violating the assumptions of regression is to make what we call a residual plot. So here we use the x values from our real data set, but now we're plotting them not against the raw y values, but the residuals, the difference between the actual value and the predicted value from the line. So in some sense, it's kind of flattening out the regression line for you. So if I show the real data with the prediction line over here, this is the data, and this is the residual plot over here. You can see it's labeled with residual. Hopefully you can see that what's going on here. So this first point here with the lowest x value, it's below the prediction line, so its residual is negative. The next one is above the residual line, so its residual is positive, and it's a larger magnitude. So this is just a different way to view the discrepancy between the predictions and the y values that we actually observed. And it's nice because it flattens things out. And you'll also notice the scale here. Here things are on a very broad scale so that we can accommodate y changing quite a bit. But once we get rid of the trend in y and we just look at the residuals, now we're sort of zoomed in and it's a little bit easier to look at the points and where they fall. And so this data set, it's tiny, it'd be hard to see a deviation from normal, but it looks pretty good in the sense that a lot of the points are close to the prediction line, so small deviations. There's a few wider ones, but they don't seem to necessarily all be on one end of the x-axis, so it's not like they all get wider in one direction or the other. So this looks like a pretty good residual plot. So I mentioned before, the assumption was not that the y's are normal, but the residuals are normal. I may not have used that terminology, but it's the deviations from the y that are deviations from the prediction line that are normal. And the residual plot is showing those deviations. So it's basically an assumption that the residuals are distributed in a normal way. So we can look at this plot and basically diagnose normality of the residuals and diagnose the fact that the standard deviation of that normal distribution doesn't seem to change a whole lot as we move across the x-axis. So here's an example from your book of looking at floral tube and a response variable. Originally, they don't show the raw data, but it's I believe it's the number of pollen grains as a function of the length of the floral tube. And here's an example of a residual plot they made, and it looks a little suspicious here. It seems to be pretty low scatter for low floral tube lengths, and then you get some really big scatter up here. And even down here, the magnitude of the scatter seems to be larger. So it seems like it's sort of a funnel relationship with the residuals as opposed to some kind of even amount of scatter across the entire residual plot. So they actually redid this regression using some kind of transformation of the y variable using a square root, I believe, and some other mathematical transformation to where they could get something that when they did the regression, it looked like they got a reasonable residual plot. This one, you see some scatter. It doesn't look like the scatter is exactly even, but you don't really expect that because of sampling error. It looks pretty good. It's pretty consistent across the length of the explanatory variable. And so, this looks fine. You could go ahead and proceed along this trajectory and sort of trust the results of that analysis. This looks very questionable here. It's basically not non-normal. So residual plots are the key tool. Residual plots and analyses of the residuals are the key tools for diagnosing whether or not we've met the assumptions of regression. Okay, so what if we fail to meet the assumptions? What do we do then? Well, as we've seen multiple times in the course, one of the first things that we can do, one of the most powerful techniques we can use, is to transform the variables so that the assumptions are met. And that's what went on in this previous example. There was a transformation. We don't see the real regression here and the transform regression, but we're just looking at the residual plots. But that's a very powerful method, and that works well and retains your statistical power. The other thing that you can do, in some cases, it's appropriate to just look at nonlinear forms of regression. So this takes us to the next section of this lecture, section 3, extensions of linear regression. Okay, so if you have, this is from your text, a relationship between productivity and number of species, it appears to be some relationship that has a peak, high values in the middle, and low values on either end. And you could fit a line, and if you fit a line, you'd probably fit something that's very close to zero slope. You might find no statistical association. But if you have more data, and it might be more compelling that you had this humped relationship here, well, there's no reason that you can't fit a parabola. So that's not linear regression anymore. This is an extension of regression. But you could say, you know what, it's the same basic idea. My model for the data is the particular y value is going to be explained by an equation based on the explanatory variable. Now the equation's gotten a little more complicated. We've got some kind of y-intercept. We've got a slope that's contributed by a linear term where just as x increases, that term increases or decreases if it's a negative coefficient there. But we can add an x squared term here. And so that would fit a parabola. If you remember your polynomial functions and the names for them. And so that's what's depicted here as a parabolic regression. And so the way I have it written here is each y value is what's coming from the linear model, plus there's some error term. That error term specific to that value, that's really just the residual. This is the expected value. The residual, we say, oh, well, there it should be normally distributed with a mean of 0 with some scatter. So that's another way of conveying the assumptions that we were talking about earlier, that the data is associated with some function of x, but then there's some kind of scatter around the prediction line. Now the equations would change for how you would find your best estimate of alpha and beta, and this is a lowercase gamma here. You have 3 parameters you'd have to fit here, and there's different mathematical tools you would use to fit those. But in principle, you can use the same idea of regression, that there'll be a prediction line and some normally distributed scatter around that line to fit almost any kind of function that you'd like to. You have to be careful with this. You can't add too many terms in the nonlinear regression. So here's a nonlinear regression with a parabola. It's just got a constant term, a linear term, and a second order term, with a squared here for x. If you add a polynomial with as many terms as you have data points, then as long as the x values are distinct from each other, you can actually draw some kind of funky curve like this one over here to the left that goes through every point. And that looks nice in the sense that there's no residuals, but really you can't trust the predictions here. Like the predictions up here are really large because the curve had to bend to come down to get this point and then back up and then get back down again. And so, this prediction is totally bogus here. If we were to drop one of these data points and refit the line in this manner, there would be another squiggly line that would go through all the data points, but it would make radically different predictions for the in-between spots. And so it turns out there's a lot of goodness of fit tests, not exactly the chi-squared goodness of fit, but similar in spirit, that allow statisticians to make this sort of decision of, if we're trying to model this data, do you use something simple like this that has maybe 2 or 3 parameters to describe it, or do you use something like this, which probably has 8 or 9 parameters to describe it? And so this is going to give the more consistent prediction, even though there is some residuals, but they're pretty small residuals here. So it seems like it's a good compromise between the simplicity of the curve and the predicted value. It's sort of beyond the scope of the course to go into how we do that, but I just wanted to make everyone aware that you can extend this idea of regression in really complicated and powerful ways, and there are even ways to make sure that you sort of prefer the simple explanation as opposed to the ridiculously complex explanation of fitting an arbitrary complexity curve. So there's a really rich literature on regression. In fact, statistics majors might have to take an entire course or two on regression, not just linear regression, but all these extensions to it, because it's such a flexible tool. Some more extensions to regression. We just talked about the non-linear prediction equations. You could have multiple explanatory variables, so you can do multiple linear regression. So what do we mean there? Now we have a couple of explanatory variables, so I've decided to say the response variable is called z here, and I'll just call the 2 explanatory variables x and y. And so the idea is now you've got a prediction for z based on some intercept plus a beta slope for x and a gamma slope for y, and there's your normally distributed scatter for each point. That's the residual for each point. So if you imagine what that looks like in 3 dimensions now, there's a linear relationship with x and a linear relationship with y, so it's sort of a plane predicting different z values. It's much more common to also include this product term to allow there to be some interaction between x and y. So another coefficient for how strong that affects things. And then you get some curvature to your surface, and you're able to fit a lot more rich data sets that way. So that would be an example of multiple regression with 2 numerical variables predicting a third numerical variable. You could do a numerical and a categorical explanatory variable predicting a numerical variable. So here's a case also from your text where we're looking at the daily expenditure of energy. It's been log transformed, and it's in social insects, I think, here, and we're looking at log body mass, and the cast of the insect is the other explanatory variable. And the cast is a categorical variable, and in this case they just have 2 casts. I don't know what they are. I just should have looked at the paper, but maybe drones or workers or something like that. And so here's an example where they've got a model that has a constant. They've got which cast you're in, so that would be whether you're the hollow circles or the filled in circles, and then you've got a mass effect. Mass is numerical, cast is categorical, and so if you're forcing only one coefficient for mass here, then these lines are going to be parallel to each other, but they don't have to be on top of each other because you want to allow the cast. So the cast effect is essentially the difference between these lines. The filled in circles seem to have a larger body mass, or lower daily expenditure for the same body mass, right? So if you look in here at some point where there's overlap between the 2 casts, the hollow circles have a higher daily expenditure compared to the filled in circles. Okay, but if you wanted to say, well, maybe there's an interaction, maybe the mass affects things, but depending on which cast you're in, there's a different slope. Then you can include an interaction term. This is not really the multiplication of the variables necessarily, unless you code them as 0 and 1, but it's really allowing for there to be a constant, a cast effect, a mass effect, and a cast by mass effect, which means you can have a line for each of them and they don't have to have the same slope anymore. And you can test whether that gives you a better fit. So once again, we're not going to require you to know how to do these in terms of the equations you would use. It gets quite complicated and everyone uses the software. But I do want you to realize that you can extend regression into non-straight lines, but also multiple explanatory variables, even multiple response variables if you've got that as well. Another really common extension to regression is when you have a binary response variable that you'd like to explain. So this is a sort of morbid example in your book of looking at mortality of guppies as a function of the duration of exposure to cold temperature. And so there was some data on brief exposure, less than 4 minutes, around 8 minutes, around 12 minutes, and almost 20 minutes there. And these are the data points in red, so you can see that only a few of them died. So it's a response variable, so all the data would be death or no death, so 1 or 0. Most of them survived at that short exposure to cold. Looks like maybe about half and half died at the 8 minutes. And so actually, the way they've done this is they've actually plotted a summary statistic of the proportion that died with a standard error here. So that's what these vertical bars are here, and the dots. So these are summaries of the data here, but also a standard error that gives you the inference if you were just treating that datum as the only data. So just based on this 12-minute exposure, that would be your best guess of the survival. But if you're interested in knowing what's the dosage that gives you like a 50% survival, you could build a prediction in here. And the way I sketched that out, it doesn't look linear, right? It's actually gonna trail off, and it's never going to quite reach 1, because the way we do this kind of prediction, it's called logistic regression, as the slide implies. What we do is we think about the prediction for yi, where that yi hat is actually the probability that the y value is a success, right? So it's that probability scale that we were talking about, of the proportion that survive, expected proportion that survive. And what we model is not that probability itself. We model the log odds of that probability. And I know that sounds weird, but we take the logarithm of the odds. Remember, the odds is the probability of success over the probability of failure. Probability of failure is just 1 minus the probability of success. And that's what we build a linear model for. So we've got a linear function here. The line isn't straight because I'm not showing you the log of the odds on the y-axis. Instead, we're just showing you the probability or the actual outcomes on the y-axis. So there's a way to transform this, and when you do that, this line no longer looks straight. But fundamentally, what you're doing is trying to fit a relationship between the explanatory variable and this log odds that scales in a monotonic way with the probability that you're interested in modeling. And so it sort of levels off like that. And that's a very useful technique, just to sort of make some sense of why we do this transformation. The probability is measured, of course, on a range from 0 to 1, but a linear function like this with a y-intercept and a slope, that can go from negative infinity all the way up to infinity. So that doesn't really work so well for modeling that directly. Well, we can think about modeling the odds. The odds, that's probability of success over the probability of failure. That could be 0 if the probability of success is 0. But if the probability of success is really, really close to 1, then this can go arbitrarily large, up to as close to infinity as you want, or there's no upper bound to how big that can be, because the denominator can get really close to 0. All right, but still, that's not exactly the range of a linear predictor. But if we take the log of it, all of the values of the odds that are less than 1, those are negative on the logarithm scale, and the closer they get to 0, the closer that goes, the more negative that gets. So there's no lower bound there. So that's essentially the motivation for saying, you know what, if we model things on the log odds scale, that's a scale that can naturally be modeled by a linear equation that has no bounds. And then we can back translate it to get this probability function, and the probability function, would eventually flatten out so that it's always a legal probability between 0 and 1. There's a linear model hidden in here. It's just not a linear model on the probability scale. So that's a really common way to look at events that are naturally or have been recorded as a binary variable. You can still use regression in those cases. Okay, now separate from how we extend regression, there's one topic related to regression that I want to mention, and it's a really complicated sort of non-intuitive topic in detail, but hopefully I can give you the sense of it and make you aware of why it's important and why we want to talk about it. It's actually one of the last things that we mentioned in the course here. It's called regression to the mean. So if you've got a numerical variable that's caused by some combination of random and non-random causes, here's the summary of the phenomenon right here. If you regress one measurement of that variable for each observational unit against a second measurement of the same variable, you might think, well, you're measuring the same thing, so the slope should be 1 because I'm just measuring the same thing twice. The regression is actually going to have a slope less than 1 if there's a combination of random and non-random causes. All right, and that may seem okay. That's surprising. Doesn't seem super important. Why are we talking about this? Well, it comes up a lot if you do things like look at the best performers from some trial. They'll tend to do worse on the second trial if it's a trial that involves even a little bit of randomness. Or conversely, if you look at the worst performers on the trial, they tend to do a little bit better on the second trial. So, there's examples of this where coaches and things like that say, well, I know my pep speech works because I talked to the players who did worse on my squad last week, and they did a lot better this week after I gave them my pep talk. And statistician says, well, wait a minute, you actually have to do a full control group in order to do that study correctly, because regression to the mean says you're going to get this kind of bias if you're focusing in on one group at one end of the range because of regression to the mean. So let's just talk a little bit more about how this works, and hopefully I can convey what's going on here. So I did a simulation, and I'm going to show you the results of in just a second. I said, let's simulate 1,000 data points, and I'm going to think about something where there's a lot of skill involved, like maybe just running a race. There's a lot of athleticism and practice, and essentially not everyone can run at the same speed. So let's just let's have a vector of skills that are going to be normally distributed with a mean of 0, so we're standardizing it to 0, and so it's a standard normal variation and a standard deviation of 1. And then I'm going to draw some kind of random effect, also from a normal centered around 0. And then I'm going to do that draw for a second random effect. And these might represent sort of the random effects that affect your skill level just on one day, one measurement. They just happen. They might be high, it might be low. You might be feeling good one day and run fast, and feeling worse and run slowly. And so, these are independent random draws here. So the first measurement is made up of how much skill you have, each one of these 1,000 units has, and the first random effect. That's going to be how fast they ran. Let's say a higher number here for this measurement means faster. And the second measurement is the same skill plus the second random effect. So we just have this mixture that I was talking about, where there's some mechanistic effect that's not random, and then there's some randomness. All right, so if we were to do a regression of skill as the explanatory variable and the first measurement, this is what I get. So skill is a variable that we wouldn't normally be able to measure. That would be like if we were able to study each person 1,000,000 times, we would get a really good sense of what their skill is. But we wouldn't know this in a normal case, so we wouldn't be able to make this plot. But if we were able to make this plot, what we see is it doesn't look like a slope of 1, but that's just because the variable, the axes limits are different in this graph. This actually is a slope of 1. In black, that's the regression line, is 102. In red is the perfect slope of 1 that we would expect because we just have random effects thrown in here. And if you look at it at some point, like some segment of the performers who are high skill, it looks like probably about half of those are above the line and half of them are below the line, because the random effects are half good and half bad because they're drawn from a normal distribution centered around 0. Same thing if we looked at some of the lower skill individuals, their random effects, it looks like there's about half as many above and below the line because the random effects are completely normal. But this is what we get if we actually sort of magically knew, had an oracle that told us exactly what the skill is for each individual when we were regressing the first measurement against those. Here's the same individuals, their same skill, but now regressed against their second measurement. Once again, the slope is very close to 1. And once again, if we look at the best performers, it looks like, roughly the same number had deviations above as below. So the second random effect was positive versus the second random effect was negative, and down here, similar thing, right? But so those two plots are sort of what you might expect. You've got some random error, but you still recover this relationship of fast people tend to be fast, and you get a slope of 1 if you regress the measurements versus their real skill. But as I mentioned, we don't normally get to measure the real skill. We'd have to, measure each individual numerous times. If we plot the first and the second against each other, so now we put first on the x-axis and second, now the one-to-one line is shown by this red line, and the regression is noticeably less than 1 is the slope of that regression, 0.51. So what's going on here? And really the key insight is the ones that do really well in the first race, that's a mixture of the high skill people and the people that had large random effects. So they did really high numbers because of their skill and their positive deviation just from randomness. And so this side of the graph here, if we look at the highest in terms of score 1, and we look at the one-to-one line, most of them are falling below that line because the reason they're in the high in the first measurement is a combination of they are skilled, but also they had positive random effects. And down here on the lower end, most of these points are above the red one-to-one line, because the reason they were low in the first measurement is because they had some combination of skill and negative random effects in this case. So if you had a negative random effect, a strong negative random effect on the first trial, it's probably going to be higher on the second trial just because most values are going to be centered around 0. So you're going to tend to do better. And down here, you're going to tend to do worse on the second trial. And so that causes the regression line to have a slope less than 1. For instance, if we look at this particular point, if I go back a couple slides, here's the skill versus the first. The highest value of the first is right here, and maybe it looks like the third highest value is actually a pretty mediocre skill level. It just has a really high random effect that boosted that individual to having a first observation very close to 4. So like one of these individuals over here, not the first one, but maybe the not the first one, but maybe the second or third, or maybe the fourth. I don't know exactly which one it was, but one of those individuals had a value near 4, but that was not due to skill. It was due to a large random effect, so that got wiped out in the second observation, and so you're much below the line for that individual there. But that kind of effect is happening again and again, and this regression to the mean is important because a whole lot of variables are described or can be described as being a combination of some real phenomenon and some effective chance. And so that means it's a really ubiquitous phenomenon. It's found in lots and lots of variables. So you have to be aware of it whenever you're comparing a non-random sample, like the best performers or the worst performers. And it complicates a whole lot of observational studies, particularly in ecology and evolutionary biology, where just the individuals that survive one year to the next are in some sense the best performers if it's a tough year where there's a lot of selection and mortality. And so in some sense you expect them to do a little worse next year because probably those survivors, even if the conditions are similar, they'll probably do a little worse because some of that was luck that allowed them to survive. And so it's very difficult to account for the effects of regression to the mean unless you have set up good controls. And so it underscores the importance of that. And when you're doing observational studies that lack a control along the time axis, and you see some phenomena that can be explained by regression to the mean, it's worth pursuing that and seeing if that's what's going on. Okay, so that's it for this sort of hodgepodge miscellaneous lecture on regression. I hope you understand some of the problems with regression, how we go about applying it correctly, but also some of the potential to use it to explore a lot of different phenomena in data sets that we can collect. All right.